Okay, so hello everyone and welcome to the Wiki 3 tutorial. I can start with the first question and it's going to be about the heating of the metal for the casting. Uh, as you learned from the topic itself that in this week we are going to discuss the casting processes. And in the casting processes, the main thing is that the metal should be changed from the solid state to the liquid state. Here we are going to learn about how to calculate the amount of the heat required to make the metal to be not only melt, but also to be raised to the pouring temperature. Okay, so the example we're going to have a look at is example 10.1 in the textbook, which is about the heating of the metal for the casting. In this example, we have 1 cubic meter of a certain etiquetic alloy is going to be heated in a crucible from room temperature to 100 degree above its melting temperature for the casting purposes. The alloy density was given as 7.5 gram per cubic centimeters. The melting point of this metal is 800 degree and the specific heat is 0.33 joule per gram degree in the solid state and 0.29 joule per gram degree in the liquid state. And the heat of fusion for this metal is 160 joule per gram. We want to know how much heat energy must be added to accomplish the heating, assuming that we have no losses. Definitely looking at the question for the first time, you know nothing. Okay, so we have to go to the theory behind the heating of the metal. So let's have background. First, heating furnaces of various kinds are used to heat the metal to the molten temperature sufficient for the casting. The heat energy required is going to be the sum of three different heats. First, the heat to raise the temperature to the melting point. Second, the heat of fusion to convert it from the solid to the liquid state. And finally, the heat to raise the molten metal to the desired temperature for the pouring. So you can see that we have the melting temperature, which is not going to be enough to change the solid to the liquid. So we need to add the heat of fusion in order to make this thing to be achievable. Third, after that, we need to add more heat to raise the molten metal to the pouring temperature to make it more soluble. Thus, it's not going to have the pre-solidification inside the cavity of the mold. Okay, so the total heat required for the melting of the temperature and take it to the pouring temperature is going to be expressed by the following equation. The first part represents the temperature required to reach the melting point. So you can see that we have the Tm in it. The HF is heat of fusion. The Tp is the temperature of the pouring, and the Tm is the temperature of the melting. So this first part is going to be to reach the melting point. HF to change it from the liquid solid to liquid. Third one is to take it from the melting point to the pouring temperature. H is total heat required, rho is density, Cs is the weight specific heat of the solid metal, Tm is the melting temperature of the metal, To is the starting temperature, usually going to be the ambient, which is 25 degrees. The HF is the heat of fusion, the Cf is the weight specific heat of liquid metal, and this will be in joule gram per gram degree. And the Tb is the pouring temperature, and the V is the volume of the metal to be heated. Now we know how to calculate the H. So let's go back to the example. When I'm going to read it, I'm going to color the parameters given to us and color coding and see what we have here. So I'm going to read back once again. 1 cubic meter, that's the volume. And from room temperature, that's 25 degree, to 100 degree above the melting points. Okay, now melting point is given here in blue to be 800 degree. And this will make it simply as the temperature of the pouring is going to be 900 degrees. Now the density is given as 7.5. The melting point is 800 degrees. Specific heat in the solid state is 0.33 the CS. The CF in the liquid state is going to be 0.29. And finally, the HF, or the heat of fusion, is 160 joule per gram. Now we just need to add that to the equation, or that's how it's going to look like. The density, the orange, the V is the volume of red. And we just keep putting that. That will be a nice thing to represent the thing. Now we continue with the calculation. Putting the figures, that's what I'm going to achieve. So you can see that I just simply change the cubic meter to be cubic centimeters, because we have the density here in gram per cubic centimeters. I put the units on purpose. So if I'm going to use my pen here, I'm going to simplify the cubic centimeters with the cubic centimeters. I'm going to remove the, here we have joule per gram degree. Here we have degree. Okay, so this will simply going to simplify the degree with the degree. Here we have joule over gram. Here we have joule over gram degree. And here we have degree. So again, to remove that with this one. Now we have G, and this will be simplified with that G. Okay, and we ending up by having the only unit to be joule. And this will be the unit for the energy. So for that, we're going to end up with having that the heat of fusion given to us is equal to 3,335 million joule or megajoule. That's the answer for the question. So the above equation is a conceptual value, but its computational value is going to be limited. Notwithstanding our example calculation, we can use the equation 10.1 above. It's going to be complicated by the following factors. First, the specific heat and the other thermal properties of the solid metal vary with the temperature, so it's not going to be constant. The CS and the CF, they are not constant, especially if the metal undergoes a change of the phase during the heating. Second, a metal's specific heat may be different in the solid state and liquid states. Most of the casting metals are going to be alloy, and most alloys melt over a temperature range instead of single temperature. And we're going to have the range is going to be between the solidus and the liquidus, rather than a single melting point like we have in the pure metal. Thus, the heat of diffusion cannot be applied so simply as indicated in the example. Fourth, the property values required in the equation for the particular alloy are not going to be readily available in most of the cases. And finally, there are a significant heat losses to the environment during the heating. So that's it for the question. That these points are going to be very useful for you to have a critical thinking in the future. Thank you for your listening, and we're going to go to the next question soon.